in yesterday one problem, they asked us to find out the difference between theoretical saturation magnetization and experimental saturation. So during that calculation, we got one experimental value, which is deviating highly from the theoretical value. And while calculation also, we neglected orbital magnetic momentum. So we got for cobalt, it has 3 mu v, and for iron, we got 4 mu v.
Iron will be for 5 MeV.
5 mu v.
5 MeV, yes. Yeah.
So upon substituting those values, we are getting the theoretical value, which is highly deviating from the experimental value.
In fact, that's the reason I had given this particular question, essentially to point you out that in many times, whatever is the theoretical value of saturation magnetization, that does not match with whatever you are expecting theoretically. Okay. See, experiment gives you a particular value based on saturation magnetization. If everything of what you say is in theory is correct, in that case you should get one particular value. Now, in theory, what we have learned are two extremes. One in which you have all the orbital angular momentum present, then you know L, and then from that particular L you calculate J, L and S combine, and you calculate J, and then you calculate the magnetic moment. Then we say that in 3D transition metals, orbital angular momentum is quenched. It means we take L is equal to, we just take it 0. We assume that J is only contributed because of S, because of the spin. Then you get a different moment. But when you actually experimentally evaluate, you get a value which is different from this. The reason is that you had neither having the situation when orbital angular momentum is completely quenched, nor you have a situation when it's not yet quenched. So it's a partially quenched system, and that's why you are getting magnetic moments value which are quite different from what you are getting as a theoretical value. And in fact, this is probably one of the reasons, one of the reasons which we give. Cobalt is a very highly anisotropic ion, which I have been telling you a number of times, that cobalt also cobalt also has a cubic structure, if I remember right, but generally comes as HCP structure, hexagonal close packed structure, which is an anisotropic structure. It has a very large anisotropy. In fact, cobalt ferrite, if you want to measure, for example, resonance, the line width will be so large that you will not be able to measure it, only because it has a huge anisotropy. Okay, so this anisotropy, because it's also related to spin and orbit thing, and therefore, essentially what to say, the orbital angular momentum is not completely quenched. So the value that we are getting from theory is not matching with the experiment. See, what essentially I wanted to point out, that generally the trend is always, that's the way it is. See, people always believe experiments. Okay, now the experimentalist, most of the time, Professor Shana is not there today as a theoretician, so I can probably speak a little bit against theoreticians. Okay. The thing is that the theorists always look at an ideal system, while experimentalists always work on a practical system. Now, practical system and ideal systems are very, very different. And in fact, one of the biggest problem has been the matching or talking in the same language. See, many times when experimentalists and theorists collaborate, this is one of the major difficulty, that one doesn't understand the language of other. They talk in their different languages. Okay, experimentalists will talk in their different languages. So there has to be a proper communication, which often is missing. More you are experimentalist, you will not understand what is meant by H Hamiltonian. I'm probably exaggerating, but this is what it means. And if you are a theorist and you say, I'm putting in transmission electron microscope, the person goes off. What is this transmission electron microscope? So this is the fact of the matter. I remember in one of the conference, there were Professor Shana says that you like to hear stories, and he said, in last class, at least tell some stories. So let me tell you a story about this. There was one particular conference long time back which happened in Hyderabad only, which I had attended. And there was a fight between a theoretician and experimentalist. So he had produced some data and got some experiment done by someone which corroborated his theory. And he was very happy about that, this wonderful, my theory I have done, and it's exactly matching with experiment. Then there is another person who was from Holland, if I remember right. He gave a data which completely contradicted his theory. So he was very upset. He said, no, all you are saying is all nonsense. It has already been experimentally measured. He says, but I have also measured experimentally. Then he asked the question, do you know what is the current in your experiment? He had no idea what is the current. The current was 10 milliamps. I'm giving the numbers which may not be correct. I'm just, exact numbers I don't remember, but the gist of the story. He says, do you know what will be the joule heating with that particular current? What will be the temperature of the sample? And that person, theoretician, just sat down, because he had no idea of what is happening there. So what essentially I was trying to tell in this particular problem, that what you normally calculate from theory, many times it differs largely from experiments. Okay? Of course, experimentalists also try to find some support from theoreticians, saying that, okay, this matches this particular theory, so therefore I think experiment, what I'm performing is a corroboration of a particular theory, but often it goes off. And many times theoreticians need to work and try to explain to it. So cobalt ferrite is one such case when you find that magnetization that you calculate from experiment differs significantly from what you would have expected from the normal systematic Ohm's rule, assuming totally orbital angular momentum to be quenched. All right, and this is ascribed by experimentalists who don't understand theory, let me be honest, that this is because of the fact that orbital angular momentum in this particular system is not perfectly quenched. And look here, this cobalt ion also showing a large anisotropy, which is also likely to be related to this particular fact. Okay. Now, I mean, this I also want to tell specifically to research scholars, because it often happens when it does not match with theory, people get worried. Oh no, might be something I have done wrong. Or theoreticians, who find, oh, my data is not matching with the data. See, the thing is that theory we are talking of an ideal system, experiment we are talking of a practical system, and there will always be differences. Okay, and let's explain. And someone of you were asking that question that particular day. So I told you, see, you always start with the simplest problem. In theory, you always start with the simplest problem. But in experiment, there is no simple problem. You have a data, you have a sample, you have to measure it. And most of the time when you start measuring, you are measuring with more defective sample. You only learn how to make better and better samples and make system more ideal. So we go the other way, while theoreticians go the other way. They start with an ideal system and they try to include some of the realistic natures and try to make it more realistic. So therefore the languages of theoreticians and experimentalists generally are very different. So the problem was essentially assigned. Don't get shocked if you're not getting a value matched with theory. In fact, one of my professors used to say, oh, then if it's not matching, wonderful, it means you have something to do. Now you have something to understand. You are probably likely to discover something new. If everything is the same line, then you have not done any research. It's like an MSc experiment. Or for that matter, high school experiment. See, you calculate G. Do you calculate G because you don't know G? Everyone knows what is the value of G. They know much better than what you can calculate from that experiment of pendulum. Okay, the idea is only to learn. All right. Similarly, if you are just doing something which is you are already expecting and you are exactly getting the same result, this is not research. I mean, that's what one of my professors used to say. Okay. Research is when you find there is something different, then you realize, oh, there is difference. Now let me try to understand it, and that's where you discover new physics. Any other questions? Feel free to ask any question, because today is the last lecture and probably it's not going to take too much of time. So you can ask any type of questions. I forgot to change. Oh, sorry. I forgot to change the affiliation. This is one of the talks which I have been at many places. So I changed many of the slides, to suit here, but forgot to change the affiliation. I should have said retired professor, which is not there. So sorry for that thing. See, there are a series of resonance experiments which we perform in condensed matter physics to get various information, which include things like electron paramagnetic resonance, nuclear magnetic resonance. And one of the lesser known of those experiments is ferromagnetic resonance, because this type of experiment is generally used only by people who are working on ferromagnetic material. But this is a very important and useful technique, and with modifications, it has lasted over ages. Even when we were PhD scholar, people were doing FMR, and even now people are doing FMR. Because some of the information that you get are very unique from this particular thing and very, very important. Of course, the setup with which we are doing resonance has changed enormously over the years, and the quality of the data that you are getting has been changed. Things that you are looking from that particular data, they have changed. So my talk of this particular thing is essentially a classical talk, which gives you just a little bit of feeling of what is the resonance experiment is, and what type of information, let's say a beginner, let's say a research scholar or a scientist who has just begun in the area of magnetism can get this particular thing. Ferromagnetic resonance is more or less similar to electron paramagnetic resonance from all point of view, almost all point of view. Except that the sample that you are using is not a paramagnetic sample, but here is a ferromagnetic sample. And irrespective of all the quantum ideas, this particular thing is always treated classically, because that's simpler to understand, though there are quantum mechanical analogs of these things to understand it, but nobody uses, even in the most latest textbook, if you are looking, ferromagnetic resonance will be dealt only classically. Unlike electron paramagnetic resonance, where they were talking of splitting of levels and things like that, and then trying transitions between them, ferromagnetic resonance is treated classically, always. See, look at my language. You apply a magnetic field into a ferromagnetic system. Before magnetization aligns itself in the direction of field, it has a precessional motion, because this particular magnetic field will apply a torque on the magnetization, which is m cross h. And because of that particular thing, the magnetization as a whole, because now I am using a ferromagnetic system, and we are assuming that the entire system can be given by one magnetization. In that sense, it's different from EPR, where you are talking about precession of individual moments. EPR also you can treat classically, but then you are talking of the precession of the individual moment. Here we are talking of the precession of the entire magnetization itself along the magnetic field. Eventually it will decay and probably align itself in the direction. That's a different question. But idea is that if you are applying a RF magnetic field, which is exactly having the same frequency as the precession frequency, then this particular precession will keep on continuing, and you will see absorption of microwaves. In fact, this frequency at which it precesses is microwave frequencies. Absorption of power, microwave power into the system. This is called ferromagnetic resonance. So as simple as that. So you have a magnetic field H, you applied out from outside in your setup. Then there is a magnetic field, unfortunately, no, this magnetic field causes precession of M, and there is RF field which is applied perpendicular to H. This results in a ferromagnetic resonance. It's a typical picture which gives rise to this particular thing. This is the magnetic field. This is the magnetic moment is precessing, and you are applying a RF field which is perpendicular to it. If it has the same frequencies, then there will be a resonance, and the precession will continue, and you will see from this precession the power being absorbed, and you can measure the frequency and blah blah other things. Now let me define certain things. Though we are talking of magnetization of the entire sample, when we are talking of ferromagnetic resonance, but we realize that there could be some reasons why the magnetization of a part of sample may be treated differently from other part. I will give those things earlier. If it is not so, then every magnetic moment which constitutes your net M will precess in phase. They will all move together, so to say. This is what we call as a uniform precession. Though in the first diagram I have described the total M, but now I am saying that these M's which are of the individual atoms which constitute this capital M, they are all precessing together in the same direction. But many times it does not happen like that. If nothing else, there is going to be surface, a boundary, and we have been talking of surface effect and interface effect in the morning, because of which you will find that these precessions at the surface may not be precessing exactly in the same way as the rest of the sample. It's something like if you want to vibrate a string, okay, if the two ends you clip together, then there will be some sort of disturbance, and not every atom or molecule of the string will be able to vibrate exactly in the same way. Okay. Of course, it's what we call, if they are completely fixed, then those points will remain stationary, but it's not completely filled but somewhat loose. Okay. Then they will probably also move, but not with the same amplitude like the other part of the sample. Just to give you a rough parallel. This is a case where you find the magnetic moments at this surface are precessing somewhat differently, at least with different amplitude. By amplitude, I mean how much is the angle they make with the direction of field. This is what is called non-uniform precession. And originally, in fact, Kittel was one of the first person who worked quite a bit about the theory of this particular resonance. The famous Kittel of the Kittel's solid state physics book series. This is also called spin wave resonance. All right, spin wave resonance in the language of resonance is normally a non-uniform precession FMR. This is what is the equation of motion, which is true for almost all the resonance, whether you are talking of NMR or whether you are talking of EPR. Use exactly the same equation, dm dt is equal to gamma m cross h. Of course, this equation is sort of incomplete because it only tells that torque is equal to the angular the torque is equal to the rate of change of magnetic moment. It does not tell you about what happens to this particular energy which is being constantly pumped in, because eventually this particular energy has to go back to the lattice. So there has to be another torque which should balance it so as to make it a particular precession, to give a sort of a steady state, so to say. So there must be a damping term which must be added to it, which will tell this particular energy, eventually whatever energy is being pumped from the microwave eventually should go to the lattice, and of course lattice will get heated up because of that particular thing. And today morning we had talked about this relaxation mechanism, how the energy from the spin system or magnetic moment system could go to the lattice. All these studies were done thanks to this ferromagnetic resonance and high power experiments, where it becomes necessary to learn or to understand how this particular energy is going to the lattice. All right. If you solve this particular equation, you get resonance is equal to omega is equal to gamma h. You know, you look at any book, I mean, they will derive it, any book on resonance. My favorite book is Accent Button, which I have told you, I think, when given the reference. It's a very old book, but if that was only omega is equal to gamma h, probably nothing much could be done with the FMR. But I have already oversold FMR earlier, right, in my first few sentences, that it can do a lot of things. Okay. So let us see what are the things that it can do. One major difference between a ferromagnetic material and, for that matter, a paramagnetic material is that the field inside the sample is different from the field which is externally applied because of the demagnetization effects. We have discussed about it earlier. In terms of shape anisotropy, when we started discussing, we say that there are some poles which are created, and those poles eventually also have their own field, and because as a result of that, the field which is seen inside the sample is different from what is external field. So Einstein, what I'm saying Einstein name came, Kittel used that particular idea and derived another equation. Now it uses something which is called demagnetization factors, about which we have not talked so far. Let me put it like that first. If you have a sample of arbitrary shape, and you have applied a magnetic field, the internal field that will be created in general may be non-uniform. All right? It means the field, which is, because it depends on how the poles are getting developed. Okay? So field, internal field here may be different from internal field here. I'm just giving an example. But on the other hand, it can be shown that if this particular shape of the sample is an ellipsoid, then internal fields turn out to be uniform. And in that case, internal fields can be presented in the form of demagnetization factors, which are called Nx, Ny, and Nz. Remember, Z is always treated as the direction of application of the magnetic field. All right? Now, when we use, I don't want to go into detail of Nx, Ny, and Z, because this itself will be a full lecture of how these Nx, Ny, and Zs are coming. Now, this is the resonance equation which Kittel derived by taking into account this demagnetizing field. Remember, this particular expression uses H, which is externally applied field, not the internal field, while resonance will see internal field. I do not want my equation to be in terms of internal field, because for that I have to calculate it. So I would rather like to have equation in terms of the field that I know, which I can measure very easily. So that's the reason I have discussed that we use H field rather than B field. All right. Now, gamma is what is called gyromagnetic ratio. Expression is G by 2mc in Gaussian system of units, which essentially uses G. Remember, we had talked about G when we were talking about the magnetic moment. So it depends on G. Omega is 2 pi f, probably all of you know, angular frequency. So it has omega, gamma, and it also has a 4 pi ms saturation magnetization. Why saturation magnetization appears in this equation? It appears because when you are going to magnetize it, okay, it will get magnetized to 4 pi ms value, and that is the one which is going to create demagnetizing field. So this resonance equation now also depends on 4 pi ms. It depends on 4 pi ms and also depends on G, and that's what makes it interesting. This can be used to measure G and 4 pi ms. Remember, when we talked about measurement of magnetic moment using VSM or squid magnetometer, we said all that we measure is EMU, total magnetic moment. It's your business to calculate it per unit gram or per unit volume or whatever you do. But this is one experiment which gives you directly magnetic moment per unit volume. Because everything is inherent in this particular Kittel's equation. That's the beauty of this experiment. If I have a thin film and you ask me to give its thickness, okay, we can measure thickness, of course. But anybody who has measured thickness knows that there is always going to, you cannot measure it perfectly. There is always going to be some error. Even if you measure at 2 or 3 different places, you know, you'll always find different thicknesses. I mean, it's known that when you're depositing film, for example, when you're depositing by laser ablation or sputtering, the film which is deposited at the corner of the substrate, that has definitely a different thickness than the film deposited at the center. In fact, most of the people discard the corners and look only at the central portion. They will cut it out and only that particular portion they will measure, because they would expect the thickness will be somewhat uniform. I mean, these are experimental realities. You know, that's what I'm saying. Experimentals, we live in real world. So these are the things, you know, in which, you know, we have to tolerate it. You know, there's nothing that we can do about it. Okay, I would like to have a better system of sputtering unit or better ablation where I deposit much better films for which we'll work and try to get it. But on the other hand, normally it will not happen perfectly. Now, if somebody asks you that you calculate 4 pi m from your VSM data, I must know the volume. For volume, I must know the thickness of the sample. And because thickness has its own inherent uncertainties, 4 pi ms will have certain amount of error. While here you are getting it directly. That's one of the biggest advantage of a resonance experiment. Of course, there are difficulties also. Not everything a platter. Nature does not give you a platter. Okay, take this particular thing and you understand everything. The difficulty is here also. So let's come to that. Please do raise questions if you are having difficulty. This particular equation, we can have two different type of extreme cases when we are dealing with thin films. A thin film, for example, could be squarish or rectangular thin film with certain amount of thickness, and by no means it's ellipsoidal. But we believe in approximations, we can approximate it. If we are taking a perpendicular resonance, we see, I forgot to tell that nx plus ny plus nz must be equal to 1. That comes by the definition of nx, ny, nz. All right? Now, because the poles are going to be very close by along this particular thickness, most of the demagnetization will occur in the z direction. So we take nx is equal to 0, ny is equal to 0, and nz is equal to 1. Substitute in that particular equation, you will get the first equation. This one. Just take this, nx is equal to 0, ny is equal to 0, nz is equal to 1. You will get this equation. Now, when I am applying field parallel to the film plane, in that case, because that's a thick direction, I can take in that particular direction demagnetization factor equal to 0. Along the z direction, that will be the z direction, and along the x direction, you will take it to be 0. Okay, then you get this particular condition, which is condition for a parallel resonance. So basically, the problem which becomes is that if you take a thin film sample, apply field normal to it, measure resonance frequency, apply field parallel to it, measure resonance frequency. Okay, you will get a value of h perpendicular, you will get a value of h parallel. There are two equations, two unknown, one is 4 pi ms, another is gamma. You will be able to get 4 pi ms and you will be able to get G. That is what is one of the biggest utility, even if you are not getting anything very special from FMR. There are many more things which you can get from FMR, about which we will be talking about. At least some of them we will be talking about. All right? So this is what is going to give you the value of 4 pi ms and G, and then of course, like we said, experimentally we'll compare whether I am getting G is equal to 2 or not. If I am getting G is equal to 2, then I know the orbital angular momentum was really quenched for the system. Okay, if I am not getting G is equal to 2, then our orbital angular momentum was not quenched. So there is that experimental measurement, and we say we always believe experiments first. All right? And 4 pi ms, now it's already ready-made available to you per unit volume. What else you want? Remember, in this case, we are still talking of uniform precision, because I forgot to mention, Kittel's equation applies only to uniform precision. There could be non-uniform precision, and if it is non-uniform precision, there could be additional contributions to this particular equations. And that makes these equations more difficult, useful, and sometimes difficult to interpret. So there are two types of non-uniform precision. There could be many types, but two, let's say, extremes. One is that your bulk itself is non-uniform, which can happen because of your deposition. Some particular ion has not been uniformly distributed. 4 pi ms itself is a function of, let's say, Z. Probably I'll be giving you some data on magnetic bubble films which we had created when I was a postdoc, okay, in which ion implantation was used to create an anisotropy, which was varying as a function of Z, as a function of thickness. And that particular thing made the bulk non-uniform. Other could be bulk is uniform, but the only inhomogeneity is lying at the surface. Surface anyway will be always present, but the surface is having enough perturbation because of whatever reason. In these two cases, the resonance conditions will become different. I am not going to derive them, but this is what is precession, and this is what is writing to mz. This equation will be in terms of mz, so which is only the z component of the magnetic moment, because once it's precessing, it opens an angle, mz will be smaller than m. For a uniform bulk, equation of motion will be given by this particular thing in case precession is not uniform. In case precession is not uniform because of whatever reason, because your spin or because of surface spins are creating some dominance effect. I will give you example of that particular thing. For example, magnetic moments could be pinned at the surface, like you pin the string and then you get different boundary condition and you get standing waves. Similar situation can be created in the magnetic system also, where you are creating standing spin waves, because the magnetic moment, what we call as surface anisotropy, I have used this particular word earlier, is so strong that it's not letting magnetic moments precess at the corners, at the edges. But the fact is that if it is not uniform, then in that particular case, there will be angle between different precession. So if one particular thing is precessing like this and another is precessing like this, okay, there will be an angle between these two. And whenever there is an angle, you have to work against exchange. Because exchange is trying to pull all the magnetic moments parallel to each other. This we have discussed in terms of domain walls when we discuss. Okay, because if you have to create a domain wall, you have to actually work against exchange, because exchange is trying to bring them together. Hence, in this particular equation, there is exchange constant which is appearing A, which is related to exchange stiffness constant by this particular expression. So now exchange is also started appearing if you are getting a non-uniform precession because of any reason, because of any reason. But this equation is valid when everything like magnetization, anisotropy, etc. are uniform across the film. But because of some boundary condition or something else, you are seeing a non-uniform precession in the system. And D, as you know, is exchange stiffness constant. If you take the dispersion relation of magnons, okay, at low values of K, it will be given on the form of omega is equal to dk square. H cross omega is equal to dk square. The standard dispersion relation which we use in case of not this particular, but concept of dispersion relation is very, very simple, which is always one of the most fundamental thing in condensed matter physics, solid state physics, because whenever you are applying boundary space, it's applied in real space. At x is equal to this, something happens which always limits you to the value of k. When you put boundary condition at x is equal to 0, let's say displacement should be equal to this much. Or when you apply periodic boundary condition that x is equal to 0, whatever is the displacement should be same as x is equal to L. It's always being applied at the real space, and that's what is going to limit the value of k. Whenever you are applying statistics, which is more important, which essentially tells you how the states are going to be filled, that is in the omega space, energy space. A lower energy state will be filled first, a higher energy state will be filled later, if I am talking of fermions, for example. Okay, so I have to go from k space to omega space. Basic problem, fundamental, condensed matter physics. You require dispersion relation. That's why dispersion relation, a relationship between omega and k, is given so much of importance in condensed matter physics. So for spin waves, the dispersion relationship at low value of k is of the form omega is equal to dk square. I'm not sure it's h cross omega, whether energy comes here or just omega, but it's of the form dk square, which essentially tells if d is larger, it essentially means the exchange is stronger. If d is smaller, then exchange is comparatively weaker. Okay, is it all right? boundary condition that we apply to solve this particular equation, this is like a Schrodinger equation, to be honest. This has to be applied by solving this equation, these boundary condition, which are called Rado-Wheatman boundary conditions, which essentially tells that dm dz should be equal to plus minus ks, is equal to plus minus ksm at the boundaries. And there are two cases, one when ks is 0, another when ks is very high. One gives you pinned condition where m is equal to 0, another is what we call as a natural boundary condition, which is dm dz is equal to 0. These are the two special equations. And in the case of non-uniform precession, you have to solve this particular equation under these two boundary conditions. And if hk and 4 pi ms are also a function of z, those equations become very, very complicated. But we being experimental, many times we have tried to solve using this particular equation. I will tell you about that particular thing a little later. If you solve this particular equation under these boundary conditions, this is what you will be getting as the field values for perpendicular resonance, which is original value was omega by gamma was h perpendicular minus 4 pi ms. Remember, perpendicular field will always be larger because there is a 4 pi ms. So it will be omega by gamma plus 4 pi ms. Now there is another field which is coming in, which is what we call as exchange shift, and that's because of the presence of the exchange, because of the angle between the space. And of course here the wave vector will be coming, and the wave vector is represented by n pi by d. And is the total number of half wavelengths excited in the film. The intensity of the modes that you will be seeing is given by this particular equation. This just looks like particle in a box wave function. The simplest quantum mechanical problem that we solve in our, probably even at first year level in BTech, at least in IIT Bombay, we teach even at first year level in BTech these things. Of course, we talk of only this particular condition because in that particular thing, the only thing what we say wave function is 0 at x is equal to 0 and x is equal to L. Here we have three different type of boundary conditions. One is what we call as a perfect pinning. Then you will have these type of modes. Another is perfect pinning on one end, another end is free. Third is no pinning at all. And because the intensity is dependent on integral of m dz, this area and this area is going to be same. So intensity will be 0 here, intensity will be 0 here, because this area plus this area is equal to this area. If you take integral m dz, that will give you 0. Okay, so in this case, there will be only uniform precession. If there is no boundary condition at the surface, then only uniform precession will be excited. But if there is a perfect pinning at both the ends, then of course this will be 0, but this will not be 0, this will not be 0. So you will have n is equal to 1, 3, 5, 7, all odd numbers of n will be excited. And there is a perfect pinning only at one of the end, you will have 1 by 2, 3 by 2, 5 by 2. These are the n values, and then you can know what are the field values. Now you can see from this thing that because of these n values which are coming here, this field depends on n square. So if I am able to observe various type of modes, if I am able to observe, then they will show you an n square dependence. When you are performing an experiment, you do not know what is the boundary condition that has been applied. Most likely the boundary condition is none of these boundary conditions, but something in between. But rather than struggling with those boundary conditions and trying to find it out, most of the experimentalists found a suitable way. That's what I will discuss. They just try to fit it with n square and try to estimate the value of t. So this is n square law, and field and intensity will not follow exactly, but it has been shown that higher order modes do follow to some extent if there is a partial filling. So there is n square law which is not perfectly followed, but higher order mode, it has been shown that it follows. So when you plot as a function of n square, which you do not know what is n, so you take various attempts and try to do as a function of n square, and whatever fits, first 3 or 4 modes will be off. So you essentially look at the higher order modes and fit a line there, okay, and the slope of that line will give you exchange constant. So this is one of the very important applications, because exchange constants are not very easily obtainable. Today morning somebody asked me, can't we do neutron diffraction? Okay, you can do neutron diffraction if you want to find out the exchange constant. But just to find out the exchange constant doing neutron diffraction is too expensive experiment. Very simple experiments can give you exchange constant, provided you see these spin wave resonance. Interpretation is complicated. If you have a non-uniform bulk, the field and the intensity pattern can be very complicated. Equations can also be fairly well involved, even for systematically inhomogeneous film. Problems relating to inhomogeneity only along the thickness can be interesting, and these are the 2 types of problems that I am listing, which are realistic problem. One is what I have called ion implanted bubble films, and another is magnetic multilayers, about which I have talked today morning, where both the components, A material and B material, both are magnetic. All right, let me just tell a little bit about ion implanted bubble film. I have used this number of times, so there might be a natural curiosity why I am talking so much about ion implanted bubble films. In morning we did talk about bubble films, and we said that these bubbles could be used as memory devices. But when these bubbles were being used, they found that out of so many bubbles, there are some bubbles which do not behave properly, misbehaving bubbles. They were called hard bubbles. See, how do you make bubbles move? You apply a magnetic field gradient, and under the force of that, bubbles will move. But all the normal bubbles will move in one particular direction when you apply, which is along the gradient direction. But these hard bubbles will move at an angle, and they can go as much off as at t degrees. And if you have a few magnetic bubbles, hard magnetic bubbles in your device, that will kill your device, because they will be misbehave, and when you want them to be read, they will not be read. They will go elsewhere. All right. So they were disastrous for devices, and they are finding a method how to suppress these bubbles. And these hard bubbles, as we now understand, was because of very complicated wall structure. The normal bubbles will have just a block wall or a nail wall, which is going from one region to another region. But these will have multiple complicated block walls, combination of block wall and nail wall. And because of this wall structure, they will behave very, very funnily. So they essentially wanted these bubbles to be, their walls to be unwinding, so that they have a simple wall. And they found that, see, I have told you that the film has a uniaxial anisotropy. That's how magnetic bubbles have to stay. On the top, for a small thickness, they will implant some ions, rare earth ions, which will put the entire lattice on the top. These are all high quality single crystals that also I have discussed. That will put the top layer into stress. And because of magnetostriction, only on the top layer the anisotropy direction will change. Now all these bubbles have to make a wall against that particular wall, which is in which the magnetic moment is not like this, but magnetic moment is aligned like this, because now you change the anisotropy direction. Okay, and they found, because of whatever reason, that hard bubbles got suppressed. Again, as an answer to the question of some people I was telling, that generally industry people don't care about physics. So they first find out a method. They needed urgently to somehow suppress it, and they found this method. Later people realized that these are the reasons why these things work. So when I was doing my postdoc, I was working on some of the materials along in collaboration with IBM on these ion implanted magnetic bubble films on the resonance of these things. So we were using resonance to find out how much anisotropy has been killed. That was our problem, on which I worked long time back as my postdocs. Not that I want to advertise my work, but it's just because, it's very old work, but it's just to tell you that, the type of variety of information that you can get from resonance. And now magnetic multilayers. Okay, these are also systematically, what I call systematically inhomogeneous. Inhomogeneities are created systematically. They are not automatically inhomogeneous. That's a different thing. They are random inhomogeneities. I have made the film inhomogeneous purposely. When I am creating a multi-layer, purposefully I have made material A, material B. Property of material A is different from material B. When I have implanted, it's purposely that I have implanted them. After all, if I have implanted, I would like to know how, what is its effect on the anisotropy. And I am looking only at a small region. Which measurement will give me that particular type of anisotropy? FMR. I am calling it by Wills and Prasad method. Wills was my supervisor there. This is the paper, long time, very old paper, 1980, I think, 80 or 81, IEEE transition of magnetics. So what we did actually, the idea was, because we didn't want to go to those complicated equations, if you really assume that 4 pi ms is a function of z, or anisotropy is a function of z. So what we did, we created artificial multilayer structure. Remember, by that time, nobody knew about multilayers. When I was doing my postdoc, multilayers were not at all known. Nobody even worked about multilayers. The concept of multilayers came much, much later. But then we created layers which are like that, imagined layers like that, and each layer that we assume the magnetic properties are uniform. Then the boundary condition is the only thing that you have to apply at each of the interface. Put a solution of that particular equation and apply a boundary condition, and larger are the number of layers, larger is the computing power required. I had told you at that time our computer had a memory of 1 megabyte, about which we were very proud. Okay, but 1 megabyte was considered as a high magnetic, computing power. Now 1 megabyte is nothing. Okay, so that type of computing power that was required was not high. So normally you will optimize a certain number of layers, you put 10 layers, 20 layers, and trying to sort of approximate so that you get reasonably good idea of how the anisotropy has changed. So these are the boundary conditions that we had used. Actually, let me be honest, these boundary conditions were not derived by me, it was derived by Professor Wills. He was really very great resonance specialist. So at each interface, you apply these boundary conditions. Solve that particular equation with natural boundary conditions at the two ends, and at each interface, these boundary conditions. We developed a program. That program was developed by me. I can take the credit of that thing. These were later modified by Hoffman. This is a French scientist. It's very, very interesting about this story. This is a part of PhD thesis of Hoffman, who never published it. When people were looking for some boundary condition, our boundary conditions had certain problems, certain issues. Okay? When they were looking at boundary conditions, suddenly they found out Hoffman's thesis, and everyone started using Hoffman's boundary condition, which introduced another constant, A12, which is interfacial anisotropy. Our boundary condition did not have any interfacial anisotropy constant. That was the deficiency of our boundary condition, because the coupling between the pair, between the two films, I could not manipulate using those boundary conditions. They were assumed always to be perfectly coupled in that sense. Now here there is a parameter A12, which you can adjust to adjust how strongly the films amongst themselves are coupled to each other. All right. So this poor Hoffman, I think, once we were trying to find out, because he worked in the same laboratory in which I had also worked as a postdoc. What happened to Hoffman? He said, no, he has left physics. After writing his PhD, he says he has left physics. So nobody, there was that particular time, somewhere in around 80s, half the paper were being published by Hoffman, using Hoffman boundary condition. And then probably Hoffman never knew that his boundary conditions have become so popular, which he wrote in a thesis which was something 10 years back or something like that. This is what happens in science. You don't know which thing becomes useful when. Wills and Prasad boundary condition means an infinite value of A12. Hoffman introduces artificial boundary. This also had some problem. This boundary conditions were also solved. In fact, there is a separate lecture one can give on boundary conditions. Let's not bother about those boundary conditions. Let's assume that there is some boundary condition which works. Now, what are the things for which this particular method can be used? Most importantly, saturation, magnetization, and G. About that, I have already showed you quite a bit. Okay. Other thing about which I have not talked about is anisotropy field. There is one big problem about this particular measurement. If your film has a uniaxial anisotropy, then uniaxial anisotropy just gets subtracted from 4 pi s. Equation just have, instead of 4 pi s minus hk. So when you do perpendicular resonance and parallel resonance, you will always measure 4 pi s by minus hk and not 4 pi s. Either you are sure that your films don't have anisotropy, then fine, you are measuring 4 pi s. But if by any chance they have uniaxial anisotropy, then you will be measuring 4 pi s minus hk. Then FMR does not have a method by which you can separate 4 pi s from hk. Cubic anisotropy, to some extent, we can separate. If it is a single stand film, that's what we had done in our paper, with which, the paper which I had, that we actually took care of cubical anisotropy, but we could not, uniaxial anisotropy was taken care in a different fashion. But if let me be honest, in that particular paper, we are not interested in 4 pi s minus hk, because we had sort of evaluated in a different fashion. All right. So problem with that is that you cannot measure anisotropy. But on the other hand, if you have an excellent measurement of 4 pi s by VSM or by any other thing, then you can use this to measure anisotropy field. But you require a separate measurement to separate out 4 pi s minus hk. People have done that when there is a growth-induced anisotropy, like for example in the case of garnet, you just heat the sample to a large extent, then most of these anisotropies get killed. Then you make another measurement, then assume that hk has become 0, then you measure 4 pi s and hk separately. The advantage of this technique is only that it's a very simple technique. See, for hk measurement, you require a torque magnetometer. I described torque magnetometer a little bit. It's an expensive equipment, and not every lab has it. Because just to measure anisotropy, most of the labs would not like to spend that type of money, unless your whole business is only anisotropy. All right. So idea is that if I can get somehow something from the a particular simple experiment, why not try? I mean, it's like using Scherrer formula for calculating the grain size. It's so simple, everyone uses that. So experimentists we tend to avoid, we tend to have shortcuts. We can determine exchange constant, we can determine homogeneity, regular inhomogeneities, we can also determine irregular inhomogeneity. If you have made your sample bad, resonance is the first thing that will tell you. You will get a very bad resonance peak. You will get multiple resonance randomly. You know that you have made a very horrible sample. Magnetically horrible. From every point of view, it may look very good, but you will find that sample is not all that great. I mean, that's also a good information. That's also very important information, that whether I have made my sample uniform enough or not. This I think I will go quickly now. Saturation, magnetization, G, you perform perpendicular and parallel resonance experiments, solve these two unknowns and calculate G and 4 pi s. The method is correct provided the resonance is uniform precision. That's very important. If it is not uniform, there is already an exchange shift, and there is no anisotropy film in the films. In case of uniaxial anisotropy, one can only obtain the difference between magnetization and anisotropy field. In case of cubic anisotropy, the equations can be more complicated, but by measuring along different axes, it can be separated out. If you have uniaxial anisotropy field, can be separated by independently measuring magnetization or anisotropy, or by killing anisotropy, for example, by annealing. Cubic anisotropy field can be separated out by carrying FMR in different directions. So you move in certain planes, which has easy axis and which has very hard axis, and separate them out. This is what we have done in our paper. This is the reference of that paper that I was talking about it, in which we have measured along. So you are going from perpendicular to parallel, and at each angle you are measuring resonance. Okay, One is taking easy access, another is not taking easy access. So you find these two type of curves from which we could determine K1. You can determine exchange constant if you get standing spin wave modes. Many times people have tried to implant just the surfaces so that actually the magnetic modes get pinned and you start getting uniform precision mode just to evaluate D. You don't have a priori any idea what are the choices of your N, number of half wavelengths. Different sets may have to be tried out, especially to fit the higher order modes. To get an absolute value of precise thickness has to be known. Temperature dependence can be found out fairly easily. So this is one of our paper long time back, again same time when I was doing my postdoc, in which we have fitted, you can see that these lines, these first 2-3 things are off. This is gadolinium cobalt sample, and you can see they are all falling as a function of n square on a straight line, which can be used to give the exchange constant value to you. All right, not easy to find it otherwise, unless you really excite spin waves and do a neutron scattering measurement and find out what is dispersion relation. This is a nickel cobalt phosphorus. This was my supervisor in my postdoc in France. But wonderful spin wave resonance spectrum you are finding out. See, just want to tell you, for those people who do not know about it, when we plot resonance absorption, you normally do not plot P as a function of H. Normally the curve should look like this. What we plot always is dpdh. It's because experimentally dpdh is the one which is made available. The signal is already differentiated. So a peak, this peak would now look like something like this. In fact, most of the, at least FMR experiments, you will see the resonance spectra in form of these type of wave, not like this. Okay, so means, look at here, this is one peak. When I say magnified by 5, it means now I have increased the gain by 5 times. So actually, in relation to this, this has to be multiplied by 5 times. Okay, so its intensity is much smaller, though it's being shown bigger. Okay, this has been multiplied 15 times. So they are very, very tiny modes in comparison to this main mode. And this experiment we performed as a function of temperature, and we could evaluate D as a function of temperature, and fit it using spin wave theories. All these were possible using resonance experiments. This is the temperature dependence of D that we have found out. It shows T to the power 5 by 2 dependence according to spin wave theory, which we could show in this particular film that it does show T to the power 5 by 2 dependence. Irregular inhomogeneities. FMR can be used to estimate the quality of the film and the extent of inhomogeneities. This is also one of our old paper. You can see most of these papers are old papers during my postdoc time. You could see these inhomogeneities. You are seeing a very odd type of spectrum, 3 peaks, which are not showing any specific intensity pattern. Actually, intensity also should go as 1 upon n square. I have not talked about that particular thing. If it is a proper standing spin wave resonance spectrum. This just shows inhomogeneity. In fact, we could determine how you should deposit the film so that the film is least inhomogeneous. FMR can also be used to characterize the magnetic films of unimplanted magnetic bubble films, about which this is again Witt's fine paper, where you can see 2 sets of modes. This set of modes is coming only from the top layer, because effectively if you calculate the 4 pi ms effective is much larger in this case because anisotropy has been killed. Actually, in magnetic bubble films, HK is much larger than 4 pi ms. So 4 pi mass effective what we call as negative. So normally perpendicular resonance is at higher field, but in the case of bubble films, perpendicular resonance will be at lower field and parallel resonance will be at higher field, because HK is much larger in comparison to 4 pi mass. So this particular layer, what we call as surface modes, is because of the modes which is in that particular layer in which anisotropy direction has been changed, and this is what we call as bulk modes, body modes. All right, and our job, which was given by IBM, which was it was an IBM project, was to look at these particular modes and tell them what is the quality of their ion implantation, how it has killed their anisotropy. That was basically our project, which could be done by resonance. This is what we found. This is how HK varies. This is constant, and this is the bulk of the film, and this is the surface layer. This is how anisotropy changes. This is how 4 pi changes. This is how exchange constant changes. 4 pi mass also changes because the ions have gone and sat there. So effectively magnetic moment per unit volume has changed. Now let's talk about multi-layers very quickly. I think I don't have time to explain, nor would I. So we recently used the same program which we had developed there. Later, when multi-layers came, we thought, when multi-layers came, oh my God, the program that we had developed during my postdoc is most ideally suited. There we created multi-layers out of a single layer. But here we are having naturally multi-layers. Why not try it out for our multi-layers? So one of my PhD students worked on this particular problem. So we took magnetic multi-layers, magnetic non-magnetic multi-layers. This is iron nickel multi-layers, 10, 10, 8, 10 angstrom, 10 angstrom, 10 angstrom iron, 10 angstrom nickel, 8 times. These are the films deposited, and these are the resonances. You can see how resonances are changing, and from that you can get an idea of what is the quality of the films and things like that. I will not go into this thing. The experimental field values are smaller than the theoretical ones. Modifications are needed to explain the field position and the exact intensity. So we found that it's not matching exactly with the experiment. This was our postdoc student who had done this particular work. Then essentially what we concluded from this particular result, that iron and nickel is actually getting diffused into each other, and that's the only way we can explain the resonance spectrum. And you can estimate what is the interlayer diffusion thickness of this particular thing. That was the idea. Let's not go into the details. Let me go to the other series. This is magnetic non-magnetic type. Niobium is non-magnetic and cobalt is magnetic, and we change the thickness of niobium layer. Niobium is 210 angstrom, sorry, 18 angstrom, 45 angstrom, 135, 410. This is, leave aside this particular, these three are the more interesting. Here cobalt thicknesses are same, 210, but the thickness of niobium non-magnetic layer is changing. All right. Now normally you would expect with 135 angstrom of niobium, the two cobalt layers would be independent of each other, because the separation between these two layers is very large. But to our surprise, we found that it still shows a mix-up resonance. These resonances are much more complicated than the type of resonance that we have seen earlier, but this is because of the fact that we are dealing with an inhomogeneous system, which we have ourselves created. Ideally speaking, the model that we have been talking is not workable for magnetic non-magnetic layer, but what I had done is assume that niobium layer is replaced by a interfacial anisotropy and applied the same condition. We agreed that, some people commented that, we should have actually applied magnetostatic boundary conditions, which are much better, but we didn't want to do it. We just wanted, our idea was to show that even with a thickness as large as 135 angstrom of non-magnetic material, the cobalt layers are still coupled. Resonance clearly shows. Not say. The field difference can be understood for an ideal material, the intensity should be 0. Okay, that's not. mean, basic idea was only that to show that they are coupled. I mean, we also obtained certain other interesting things, but otherwise it will be big talk on resonance only. So my last slide is why FMR, very sensitive, can be used for very thin films. In fact, when we are talking of ultra thin film, FMR was the only technique, because FMR was used originally for EPR. And EPR is paramagnetic material, which has a very small magnetic moment induced. Okay? So if you have even a small material which is ferromagnetic, you will get a good signal. So even for ultra thin films, FMR was used, where your VSM will fail. Problem with squid, etc. Squid probably will work, but you have a huge substrate behind it. What are you going to do with the substrate? That's also going to give you a signal. See, no material is perfectly non-magnetic. It has to be at the most diamagnetic. That also has its own signal. All right? Can give many information easily, like exchange constant, inhomogeneities, interlayer coupling, etc. These are the people with whom I have worked. I have not put Professor Wild's name, he's no more, but there's only one paper which I have quoted from him. Thank you. So this is by the end of FM. If you want to hear any other stories or anything about it or ask any questions, you are most welcome. Yeah.
Sir, I've heard that there is antiferromagnetism in high TC, in high temperature superconductor.
Okay.
So can you tell me more about it?
Of course, that's not really related to what I'm doing. See, basically every I'm not sure about antiferromagnetism because I've definitely not heard. Only thing which we know is the Meissner effect, which shows that a superconductor acts as a perfect diamagnet. But to be very honest, I'm not aware of that thing. My area, I think, should ask Professor Shenoy because he's the superconductivity expert. He should be able to answer whether there is an antiferromagnetism which has been seen along with the superconducting.